Hello students, myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the series of optical communication lectures, I am going to deliver before you one of the attenuation parameter, one of the parameter which leads to the loss in the optical communication, that is scattering loss. In this section, first of all we will study about the scattering loss, then the types of scattering loss, and within the types of scattering loss we will discuss about the linear scattering loss, Rayleigh scattering and the Mie scattering. So, now first of all the scattering loss, as the term denotes, that is the scattering. That means we are distributing something. Scattering itself means that whatever it is, whatever signal is coming, and what if it get in conflict with something in their path, that it get distributed in a random manner. And that is called the scattering. It comes under the attenuation or the loss parameter in the optical communication, because in this way it will distract the direction which is provided to it initially, first of all. And if the direction in any type of communication, direction plays a very important role. If any signal get distracted from a direction, that means it does not obey its originality, and whatever information we are getting at the output is not exactly which we want. And also another thing, that it does not beneficial for the secure communication. If the direction get disturbed of any signal, the secure communication is not possible, which is a very important parameter whenever we talk about any sort of communication. The third one, the signal which is coming have some amplitude, has some intensity, but if it get distributed, that means original intensity is not retained by the signal now, and it is distributed now. So, also we can say that if it has to cover, for example, 1 kilometer, if at initial it is designed to cover the 1 kilometer distance, then it will not able to cover that, it will attenuate in between somewhere before 1 kilometer. So, that is why it comes under the category of attenuation or loss, etc., in the optical communication. Now, back to the scattering loss within the optical communication. Scattering loss are caused by the interaction of light with density fluctuation within a fiber. So, as already told about the scattering, that whenever some obstacle comes in the path of a ray of light or any signal, it gets scattered. The same thing is happening in the case of scattering loss in optical communication. Scattering loss is caused when there is some density fluctuation, and density fluctuation itself means that originally it has this intensity, for example, and if we increase the density, then of course it proves to be an obstacle in the path of ray of light, because originally it has to cover only this much density, and if we increase or decrease the density, then its path get disturbed and it get distracted and scattering occur. Density changes are produced. So, how the densities changes are produced within the optical fiber? Optical density changes are produced when optical fiber are manufactured. So, this density change are itself produced within the optical fiber when it is manufactured. During the manufacturing, region of higher and lower molecular density area relative to the average density of the fiber are created. So, during the manufacturing process or during the fabrication of the optical fiber, somewhere lower density and somewhere higher density of molecular density areas get created. These are actually manufacturing defects which are either higher molecular density or lower molecular density than the average density of the fiber, and this will lead to the obstacle in the path of optical signal and leads to the scattering loss. Light travelling to the fiber interact with the density area and partially scattered in all direction. So, this is basically the scattering loss which occurs due to density fluctuations which get occurred in the optical fiber during its manufacturing process. Now, back to the types of scattering loss. Basically, there exist two types of scattering loss. First one is the linear scattering loss and the second one is the non-linear scattering loss. So, linear scattering loss are those scattering loss which follows the principle of linearity, and non-linear scattering loss are those which does not follow, that means non-linearity principle. In the linear scattering loss, there exists in any type of linear system, we can say there exists a linear relationship between the output and the input. So, varies linearly with the input in this case also. We are going to discuss about this in detail in the further slides, and under this category we will have, under the linear scattering laws, we will study Rayleigh scattering and the Mie scattering, and if this comes under the linear scattering laws, that means it will also follow the linearity principle. Now comes the non-linear scattering laws, about which we will discuss in the next lecture. In this non-linearity, that is output versus input relationship is non-linear. And in this there are two types. First one is the stimulated Brillouin scattering, that is also called as SBS, stimulated Raman scattering, that is SRS. Most generally it is called as the stimulated Brillouin scattering is called as the SBS, and the stimulated Raman scattering is called as the SRS. Now, linear scattering. Linear scattering mechanism causes the transfer of some or all of the optical power contained within one propagating mode linearly into the different mode. That same thing, that is, in this mechanism, whenever we take text, first of all have an again the recap of the scattering. Scattering loss occurs when there is some changes in the normal path which is existing during the propagation of the light signal. When the changes occur in their path, propagation की path में अगर कोई changes होते हैं, then scattering loss will occur. So, अब जब भी ये path change होता है, scattering में जब भी path change होता है, path में disturbance आता है, then in any case there is a change in mode also. Whenever, always we have to keep this in mind, then whenever there is a path change in the light propagation within the optical fiber, then there also mode of a optical fiber changes in that case. So, in this linear scattering loss mechanism, what is going to be happen? That is, of course, linear scattering loss causes a transfer of some of the or all of the optical power propagating within one mode linearly, as the name indicates, that is, relationship should be linear between the output and the input. The proportional to the mode power into the different mode. That means in this particular mechanism of scattering loss, energy or the power get transferred from one mode to the different mode linearly. That is, linearly, whenever any system is linear, that means it has to be proportional to the input parameter. That is why we can say that output varies linearly with the input. That is why here it is mentioned proportional to the mode power, which is the initial power. This process tends to result in attenuation of the transmitted light. That is why it comes under the category of attenuation, as the transfer may be leaky or radiation mode. Already discussed in the previous lecture that whenever we have a core and the cladding structure of the optical fiber, the ray which is propagating, it is called as the propagating wave. Propagating comes under the propagating wave mode, which is remains inside the core and does not go outside the core into the cladding. But if some ray go outside the core into the cladding, then it comes under the category of leaky or the radiation mode, and this does not contribute to the propagating signal. So, at this, the ray which is coming, first of all it is in propagating mode, but when they get scattered, it is the chances that some of the signal will comes under the leaky or radiation mode. Because it is possible that it comes under the cladding region. And if any signal comes under the cladding region, that will contribute to the attenuation or the loss. So, same thing is mentioned here. Attenuation as a transfer may be leaky or radiation mode, which does not continue to propagate within the fiber, but is radiated from the fiber. That means, if did not continue to be propagated within the fiber, then it will not contribute to the propagating mode and it will result into the radiation or leaky mode. With all the linear process, there is no change of frequency. There is one of the important difference between the linear and the non-linear scattering loss. In the linear scattering loss, there is no change of frequency on scattering. That means, whatever be the signal of the starting, whatever be the frequency of starting signal, after getting obstacle and get scattered, all will have the same frequency. Linear scattering may be categorized as, this scattering may be in backward direction also. This linear scattering may be categorized as Rayleigh scattering and the Mie scattering. So, we have always keeping this in mind that no change of frequency and the linearity will also exist in this too. The basic principle which is applicable to linear scattering loss is also applicable to this one. Now, the Rayleigh scattering. So, it is a dominant intrinsic loss mechanism in the low absorption window between the ultraviolet and the infrared absorption tail. It is a dominant one. First of all, in the low absorption window, we have seen that as per the optical window, there also exists a loss graph with respect attenuation and the there exists a attenuation and the wavelength relationship. It is not possible that that in each wavelength there will be equal attenuation. Attenuation varies as per the wavelength. As in some wavelength it will attenuation will be greater, and in some wavelength attenuation will be minimum. So, we have to always consider that we have to make our propagation possible, optical propagation possible only in that window of wavelength where there is low attenuation. So, before proceeding or before selecting for any frequency, any band for optical communication, first of all we have to check whether it lies in which window. If it lies in the higher range of attenuation, then we should not accept that, and if it is lied in the lower range of attenuation, then only we will use it for the optical communication. So, it is the Rayleigh scattering is a dominant intrinsic loss mechanism in the low absorption window. That means, in the lower absorption window between the ultraviolet and the infrared absorption trail, this is one of the most dominant loss mechanism. It results from the inhomogeneities of random nature occurring on a small scale compared with the wavelength of the light. It occurs in the due to inhomogeneities of the random nature, or when the inhomogeneity is small as compared to the wavelength of the light. So, whatever deflection, what we are talking about in the scattering, that some changes occurs within the fiber, either in the material of the fiber, either in the construction of the fiber, it is possible. So, whatever deflections, whatever inhomogeneities which exist in the metal or in the optical fiber should have a wavelength small as, should have a length basically as compared with the wavelength of the light for the Rayleigh scattering. Again I am repeating कि इस case में for the Rayleigh scattering to happen, whatever be the dimension of the obstacle, that should be less as compared to the wavelength of the light at which the propagation is undergoing. This inhomogeneity manifests themselves as the refractive index fluctuations and arise from density and compositional variation. So, अब सम ये exactly होता क्या है basically inhomogeneity arise कैसे होता है? Whenever there is a density and compositional variation exist within the optical fiber. So, of course, refractive index fluctuation will also exist. This is not possible that if we have a, for example, if we have a silicon and it has a N1 refractive index, and in some level, but as it get combined with any other metal, for example A, and another element, for example A, in a small quantity only, it is not possible that its refractive index will remain as N1. It will definitely change to N1 dash. And also, when there exists a S A, but here there is a higher density, then also in that case also refractive index will change. So, this homogeneity arises due to variation in the density or the compositional variations within the fiber, which leads to the refractive index fluctuation. This compositional variation may be reduced. So, there is a chance, there is a way to reduce this particular scattering loss by this compositional variation reduction. So, this compositional variation may be reduced by improved fabrication. If we improve the process of fabrication, so that any other element does not indulge into the original element during the fabrication process, we should reduce this particular loss. But the index fluctuation, that is refractive index fluctuation, which is caused by the density inhomogeneities, cannot be removed. This is a fundamental loss and it will exist. Now, here when we say that output varies with the input parameters. So, what will be the input parameters according to which output will vary? The scattering due to density fluctuation which occur in all directions. So, we have already known that compositional variation may be reduced by fabrication, improved fabrication process, but density fluctuation which leads to the index fluctuation further will not be reduced. So, that is why here it is mentioned scattering due to density fluctuation varies with respect to the 1 by lambda to the power 4. That is why Rayleigh scattering coefficient is written as gamma r is equal to 8 pi cube divided by 3 lambda to the power 4, variation with the 3 lambda to the power 4 and to the power 8 refractive index, p square which is average photoelastic coefficient, beta c which is isothermal compressibility at the some temperature, Tf is also here, K is your Boltzmann constant, these are the formula for calculating the Rayleigh scattering loss. After that, transmission loss factor can be calculated with the help of our Rayleigh scattering coefficient, where it is equal to exponential minus gamma r into length, which is our transmission loss factor, and after getting the transmission loss factor we can able to calculate the attenuation, which I am going to discuss with you in this particular numerical. So, what is given in this particular numerical? That silica has an estimated temperature, that is Tf equal to this one, has an isothermal compressibility. Isothermal compressibility is our beta c. So, this is our beta c. Refractive index and the photoelastic coefficient, that is N, refractive index is 1.46 and our photoelastic coefficient, which is represented at P, is equal to 0.286 respectively. Determine the theoretical attenuation in decibel per kilometer due to fundamental Rayleigh scattering at 3 different wavelengths, 0.663, 1 and 1.3 micrometer. Boltzmann constant is given as this one. In this particular class, I will discuss only for the one wavelength, that is 0.63 micrometer, and for this and this is left as an assignment for you, answer is provided. So, I am going to have the for 0.63 micrometer. So, first of all I have calculated the Rayleigh scattering coefficient. For that I have just written the formula first, gamma square r is equal to 8 pi cube n to the power 8 p square beta c k T1. Already discussed what is the name of the nomenclature of the all the parameters here. Just put it on the formula, pi value is known, n is 1.46 n to the power 8, p square which is our photoelastic coefficient 0.286, beta c compressibility, that is 7 into 10 to the power of minus 11, K Boltzmann constant, value is written here 1.381 10 to the power minus 23, temperature is 1400 Kelvin. By putting all the formula, we will get a general formula for the Rayleigh scattering coefficient in the terms of lambda to the power 4. We have taken the general formula because we have 3 different wavelengths. We can use same formula for calculating the Rayleigh scattering for coefficient for all three wavelength. Now, as already told to you that I will calculate only for one single wavelength, and for rest of the two you have to calculate. So, if we put lambda, that is 0.6 micrometer, we get the Rayleigh scattering coefficient as this one. Then transmission loss factor for 1 kilometer, by putting the value 1 kilometer, that is 10 to the power of 3 meter. By putting this value, and we get this one, and whatever value we are getting from this, if we put in the attenuation formula, that is 10 into log to the base 10, 1 upon transmission loss factor, we will get this as the answer. So, this I have done for you. For rest of the two wavelength, you should solve it. Now comes the Mie scattering. This is also a linear scattering which occurs at the inhomogeneities. But for this, inhomogeneities has to be comparable with the size of, with the guided wavelength. In the previous section, that is for Rayleigh scattering, inhomogeneity should be small as compared to the wavelength, but here inhomogeneity should be comparable with the guided wavelength. Now, this result from the imperfect cylindrical structure. Rayleigh scattering is occurring due to density fluctuation or compositional variation, but this particular Mie scattering, which comes under the linear scattering and follows the linear principle, occurs due to imperfect cylindrical structure of the waveguide and may be caused by fiber imperfection such as irregularity in the core cladding interface, core cladding refractive index difference along the fiber length, diameter fluctuation, strains and bubbles. So, what is the basic difference? जो आपका Rayleigh scattering है, that is due to changes in the material which are used, but this are due to any change in the structure of the fiber which we are using. Irregularities in core cladding interface, refractive index difference along the length, diameter fluctuation. So, these are the responsible for the Mie scattering. But one important difference which I have told you, Rayleigh scattering occurs in all direction, but Mie scattering prominently occurs only in the forward direction. If it occurs in the backward direction, it is of very less magnitude. Depending upon the fiber material design and manufacture, it causes the significant loss. It can be reduced by removing imperfection due to glass manufacturing, careful control extrusion and the coating of the fiber, increasing the fiber guidance by increasing the relative refractive index difference. These are the process to minimize the refractive index Mie scattering. This is the one of the pictorial representation. This is the Rayleigh scattering occurring in all direction. This is a Mie scattering occurring in the forward direction prominently. In the backward direction, it is very less. Particle size has to be less than the wavelength. Another difference, non-angle dependent. It is angle dependent, and which we can see most prominently in the when the obstacle size is big. When obstacle size is small, angle dependency can be seen not clearly, but you can see that when the obstacle size is increased, angle dependency is clearly seen. So, this comes the end of a linear scattering loss. In the next lecture, we will discuss about the non-linear scattering loss. Till then, keep on studying. Thank you.